We often dream of climbing to the heavens, but now we are finally learning how to weave the rope. The vision of the space elevator. For decades, the idea of a space elevator was pure science fiction, a vertical railroad to the stars, grand, elegant, and utterly impractical. But science fiction has a habit of becoming science fact, and the last few decades have seen a quiet revolution in material science that may turn this dream into a pillar of our civilization. We've looked at this dream before, first in our deep dive on strategies and current progress, and again when we explore the economics of getting it built. But today, we're pulling all those threads together and following the ribbon from Earth to orbit, from lab to launch. A space elevator promises to replace the roar of rocket engines with the hum of electric motors, the flash of ignition with the glint of sunlight on a ribbon stretching from Earth's surface into the black of space. And like all grand engineering projects, whether the Roman aqueducts, the Transcontinental Railroad, or the Internet, it's not just about getting from point A to B, it's about changing what A and B even mean. Because a space elevator isn't just a new way to get to space, it's a foundation for building in space. Once you are hauling hundreds or thousands of tons to geostationary orbit each day, suddenly habitats, solar farms, shipyards, and even moon-bound transports become not only practical, but commonplace. Of course, for that to happen, we need two things: the right material and the right math. The rope must be stronger than steel, lighter than aluminum, and longer than anything we've ever built. And it has to make economic sense too. Even a bridge to the stars still needs someone to pay the toll. So in this episode, we are going to explore how that miracle rope might actually be manufactured, what it would cost, and how it might change not just how we go to space, but how we live and work there. And maybe, just maybe, how we start to belong there. In a way, this episode is a sequel, not just to our earlier explorations of space elevators, but to our dive into graphene's revolutionary potential. Back then, just 5 years ago, it was mostly theory. Today it's prototypes, production methods, and megastructure math. We are not just dreaming about the future anymore, we are drawing up the blueprints. It's also part of our broader journey through the world of megastructures and advanced materials. From Dyson swarms and orbital rings to clock tech like magmatter and nanofibers, these concepts don't stand alone. They form a latticework, each one reinforcing the others, making the improbable more practical and the impossible just a little more inevitable. The rope that reaches the sky. The most famous part of a space elevator is the tether, an impossibly long cable stretching from the equator up past geostationary orbit. But what's less often appreciated is just how absurdly strong that cable needs to be. Not strong like steel, not even strong like Kevlar or carbon fiber. These will work on our moon or other places of low gravity, but we need more to leave Earth. Every material has a breaking length, the length at which the material can hold up its own weight, and our tether will be stretching 100,000 kilometers. Low gravity as we get away from Earth helps us quite a lot, but we still need something very impressive. This is where materials like graphene, carbon nanotubes, boron nitride nanotubes, and graphene superlaminate come in. A single layer of graphene is just one atom thick, arranged in a honeycomb lattice of carbon atoms, but what makes it astonishingly strong isn't just the carbon, it's how tightly those atoms are bonded. Each carbon atom is covalently linked to 3 others in a perfectly symmetrical pattern, with bond lengths of just 0.142 nanometers, some of the shortest and strongest bonds found in nature. Similarly, hexagonal boron nitride, where half of the atoms are boron and the other are nitrogen, has a bond length of just a hair higher, 0.145 nanometers, and is another remarkably strong 2D material. Single crystal graphene is just that, as has a breaking length of 6,366 kilometers. This incredibly tight atomic spacing means the structure has almost no room for deformation. Defects struggle to spread, and even small areas can carry immense loads. This results in materials with theoretical tensile strengths upwards of 130 gigapascals, around 100 times stronger than steel by weight. It's not just a strong material, it's a textbook example of what strength can look like when built atom by atom. Now, that's the theory. In practice, we are not making flawless monocrystalline hammocks yet, but we are making polycrystalline graphene, patchwork versions with slightly lower tensile strengths, typically in the 60 to 100 gigapascals range. Still far stronger than a conventional material, and with rapidly improving manufacturing methods like chemical vapor disposition (CVD), we are already producing ribbons and sheets that are meters long and millimeters wide, instead of just microns across. They are still thin as saran wrap, but they are growing. What matters more than peak performance is breaking length, the point at which gravity would snap a dangling cable or ribbon under its own weight. Steel has a breaking length of only 25 kilometers. Kevlar might get you to 200. Again, graphene can hit 6,366 kilometers maximum, which actually is more than good enough for a space elevator if you taper the tether smartly, adding width and layers towards the top where tension is highest. Gravity drops as we move away from Earth, and that, combined with a taper design, lets us extend the tether well beyond what its breaking length would otherwise be. And yes, even imperfect graphene may be good enough, because this isn't just a matter of raw strength, but of density and scalability. Multi-layered single crystal graphene is 2.299 grams per cubic centimeter, about the same as plastic. Its strength-to-weight ratio is so extreme that we could build tethers with redundancy, bundling multiple sheets or strands to improve durability without losing viability. But it's not just about graphene. Carbon nanotubes, rolled up cylinders of graphene, bring different strengths to the table. They have superior elongation properties and can form fibers with less defect propagation, which may make them easier to spin into cables. And boron nitride nanotubes, while not quite as strong, are electrically insulating and thermally stable, making them good candidates for protective sheathing or hybrid designs. Like graphene, boron nitride in 2D form benefits from tightly bonded hexagonal lattices, though with different atoms. This gives it strength, flexibility, and resilience in harsh conditions, from higher temperatures to ionizing radiation. They also have a higher coefficient of friction, which makes them easier to grip than graphene, a useful trait when building something you want climbers to stick to, not slip off, so they can push and pull themselves on it. The real trick lies in dimensionality. As a true two-dimensional material, graphene has no loose ends. Forces are distributed evenly across its sheet-like structure. That's what makes it not just strong, but remarkably efficient at staying strong under tension. Needless to say, that level of atomic perfection is hard to manufacture at all, let alone in bulk. And that's why we're not already weaving tethers to the stars, because building a 100,000 kilometer ribbon isn't just a materials challenge, it's a manufacturing revolution. Even so, we are making real progress. Graphene-enhanced materials are already in the market: concrete roads with better durability, longer-lasting batteries, and flexible electronics. Production is climbing the S-curve from lab scale to industrial throughput. The Graphene Engineering Innovation Center in Manchester, GEEK, and other research centers are now producing graphene sheets fast enough to matter, meters per minute, and with tolerable defect rates. The price has dropped by orders of magnitude in the last decade, and the curve is still bending. Combine that with smart design and practical testing, like suspending early ribbons from high-altitude balloons, or laying them out flat to stress test their tension profile, and we may soon be ready for our first real tethers, not the whole 100,000 kilometers, but enough to learn. Because the miracle isn't just in making something strong, it's making something strong enough, cheap enough, and reproducible enough to scale. And graphene, CNTs, and even boron nitride all have one huge advantage: they're made of common atoms. Carbon is one of the most abundant elements in the universe. Unlike rare earth metals in your smartphone or the cryogenic ice of Europa, this is an easily accessed and abundant homegrown material. You don't need to fly to Titan to get it. You just need a lot of carbon, of which we have an abundance all around us, and a way to organize it very, very well. So we're not just waiting for some magical unobtainium, we already have the ingredients. Now, we're learning to cook. Manufacturing the megastructure. Now that we've got the ingredients, how do we bake the cake? Manufacturing a space elevator tether is less like forging a chain and more like spinning an incredibly long, ultra-thin ribbon with precision at a planetary scale. The process must be precise, defect-tolerant, and continuous. Even minor imperfections, microscopic voids, misaligned bonds, can compromise strength. And we don't just need one ribbon, we'll likely need dozens or even hundreds of parallel or bundled tethers, woven together for strength, redundancy, and modular repair. You can either make a thicker tether that carries more weight or build more of them. Ground sites are almost trivially easy and inexpensive, so scaling horizontally, adding more elevators, is also a viable approach. Either way, each tether must be as flawless as the last. There are two broad approaches to making the tether: fabricate it entirely on Earth and launch into orbit, or construct it in orbit and from raw materials delivered from Earth, or harvest it in space. Both approaches come with challenges. The Earth-first method assumes we'll develop lightweight tethered payloads that can be launched aboard next-generation rockets, like SpaceX's Starship, or lifted in stages by conventional launch systems. This could involve pre-spooling the tether in a compact roll and unfurling it down to Earth from geostationary orbit, possibly from a counterweight satellite deployed first. The critical challenge is weight and size, launching something strong enough and long enough to serve as a starter ribbon. But it is a feasible entry point, especially if our early tethers are just enough to support test climbers or serve as anchors for larger structures. In the long term, however, orbital manufacturing has clear advantages. Microgravity simplifies layer-by-layer deposition, reduces contamination risks, and allows us to use raw carbon feedstock directly from other celestial sources, or even Earth itself once you have an elevator, if it turns out microgravity is a better place to make the material. We have found graphitic inclusions on meteorites, suggesting graphite may be readily available in carbonaceous asteroids. The Moon is less promising in this regard, though Mars offers better prospects, especially as it has methane in the caps. Earth has plenty of sources of many types, and in fact methane and other carbon gases are our preferred feedstock at the moment. Making graphene powder from graphite is easy. Making graphene laminate and superlaminate from graphite is incredibly hard and energy intensive. Early tether production will likely rely on scalable domestic manufacturing plants that refine graphene from feedstocks. These facilities are already expanding, often designed to serve both space and terrestrial markets. Graphene-enhanced asphalt, concrete, and polymers all benefit from the same production pipeline, and economies of scale will accelerate adoption. Techniques like chemical vapor disposition and World War synthesis are already producing meter-scale graphene sheets, and advances in polycrystalline layering mean we're finally crossing the line from lab curiosity to industrial product. At a certain point, we may move the entire manufacturing chain off-world. Methane is even more abundant in the outer solar system than the inner one, and carbon abundant almost everywhere. Graphite is not likely to be rare. It's thermodynamically favored in some planetary and asteroid environments. Some carbonaceous asteroids might be bricks of the stuff, so we can source our material off-world, and even the spools themselves, those massive reels of nanostructured ribbon, might be made in space, then shuttled to orbital assembly yards for tether deployment. Because if there's one thing a spacefaring civilization will always need, besides air and water, it's strong, cheap, scalable material. And carbon, as it turns out, may be our greatest ally in turning our dreams into infrastructure. Tether design and variants. So let's say we get our graphene or our carbon nanotubes fresh from the factory. Now what? Designing a space elevator tether isn't just about choosing the strongest material, it's also about how you arrange it, how wide it is, how it tapers, how it handles vibration, thermal expansion, ionizing radiation, and micrometeoroid impacts. Like building a bridge or a skyscraper, architecture matters as much as the ingredients. The current favorite concept is a ribbon, a wide, thin band, not unlike a roll of packing tape or gift wrap. This shape spreads tension across a broad surface and makes the tether more visible and trackable, which helps with navigation and safety. It is worth remembering that sheets or strings of this material are like razor-sharp cords hanging in the air. We want to minimize things flying into them to protect both the tether and the thing it's sliced in half. A ribbon also provides a flat surface for climbers to grip or inductively power themselves against, but a ribbon is not the only option. You could build a cable, round in cross-section, like a traditional wire rope, or even a perforated sheet, engineered to reduce mass and flex under load. The exact method might depend on manufacturing methods. Roll-to-roll production favors flat ribbons, while spinning fibers into threads may nudge us toward braided or cable designs. Air pushing on a wide flat ribbon is a potential issue, though you can probably rotate it perpendicular to the airflow or use a cable in the atmosphere and a ribbon the rest of the way up. There's also the matter of tapering. A tether experiences the most stress in the middle, right around geostationary orbit, where gravity below and centrifugal pull above are both tugging hardest, so a smart design tapers the ribbon, thinner at the ends, thicker in the middle, like an upside-down bridge suspension cable. This uses less material without compromising strength. Climbers present another design challenge. Unlike a steel cable, you can't just grab on. Space elevator tethers will be microscopically smooth and slippery, and in some cases razor sharp. A traditional roller or gear system would wear out quickly or damage the tether. That's why many proposals lean toward magnetic adhesion, electrostatic traction, or even Zamboni-style rolling contacts that minimize wear while generating power for the ascent. We also don't really know how slippery the material is till we build it in bulk. There is good reason to think it will have a higher frictional coefficient, or can be made to have one. Redundancy is vital. Rather than relying on a single ribbon, we will likely bundle many strands together, each one sharing the load and backing up the others. If one strand gets damaged, others can take the load. This modular design also helps with maintenance and repair. Damaged sections can be reeled in and swapped out like printer tape or conveyor belts. We might even set up maintenance bots to crawl the tether, inspecting, patching, or swapping parts robotically. Graphene appears to be easier to repair than carbon nanotubes, which might make it better for this role. We also have to ensure that cables or ribbons do not bump into each other, which might be done by putting the occasional spacer between them. We may also want to be running power cables along these, especially thicker cables that can handle the much larger weight of a high voltage cable thousands of miles long. Though graphene, CNT, and BNNT all have interesting electrical properties that might let them serve as part of a power relay, letting us send power down from space-based solar arrays at the geostationary hub or up from ground-side reactors. Alternatively, we might put microwave beaming receivers on the side of the crawler. Ideally, you do not want the crawler carrying fuel or batteries except as backups, but there's likely more than one way to make this work, and some may work better for different applications and crawler sizes. And let's also not assume there's only one way up. You might deploy several parallel tethers from the same anchor point, each one optimized for a different task: heavy cargo, light express freight, or passenger travel, or even use multiple anchor points. After all, the Pacific Ocean isn't short on equatorial real estate. As we mentioned last month's look at space elevator economics, when climbers are departing daily carrying tens of tons of cargo, or upgraded versions hauling hundreds of tons or multiple climbers per day, they could easily be anchored to the smallest class of container ship. With only modest retrofitting, these vessels could provide ample operating space, warehouse capacity, and living quarters for crew and inbound passengers, all at a fraction of the total system cost. Once a single elevator is operational, every nation with even modest space ambitions will likely want one. Within a decade, they'll either have their own or be renting time on a privately owned tether. These systems don't have to sit precisely on the equator, and there's room for tens of thousands of installations along it without overcrowding. You'd likely end up with four principal types of tethers: low-capacity cargo lines lifting 10 to 60 tons, super heavy tethers for bulk cargo or oversized equipment, perhaps multiple ribbons supporting large container-like climbers, passenger dedicated lines focused on speed and radiation shielding, likely in the 100-ton class or higher, and finally, dedicated down lines, used for returning people and the occasional high-value object we no longer want in orbit, or maybe even gold from asteroid mines. We might also see bundled tether designs, where each climber grabs multiple cables at once and can switch between them, enabling climbers to pass one another going up or down. That adds complexity but also flexibility, and flexibility is the key to scalable infrastructure. A lot would depend on the practical engineering of the tether, which ultimately comes down to materials, and we simply don't yet have large enough quantities of them to conduct the kinds of hands-on experiments needed to gather first-hand data and experience. It is hard to predict the economics of continental railroads made from steel when the only steel in existence is a few pieces of steel foil or nails. In time, we could see tether farms, dozens or hundreds of parallel elevators, forming a carbon ladder rising into space. As mentioned, they wouldn't even need to be equatorial necessarily. While the physics is simpler at the equator, non-equatorial tethers may be viable with counter-tether systems or orbital balancing tricks. These would require more mass and complexity, but they could offer space access from populated regions or existing infrastructure hubs. That could allow tethers direct from places like New York, Tokyo, or London. But even near the equator, you could have two anchor ships, one 10 miles north, one 10 miles south, sharing a terminus or midpoint station, each with its own tether connection. And they can go on land, too. We just have to be clever on how we set up our traffic and wanting to keep adding more tethers to meet demand and in a way that doesn't tangle them. At a certain point, you could have enough cable to carry every human up to space every day if you wanted, allowing millions of tons of cargo. And that's the real strength of a smart design. It doesn't just make a space elevator possible, it makes it adaptable. We're not just building one magic ribbon. We're building the first real infrastructure for reaching space. something we can upgrade, adapt, and scale as we go. Before we wrap up today's exploration of highways taking us off-Earth, let me recommend something a bit more down-to-Earth, protecting your own digital world and your access to the information superhighway with today's sponsor, Private Internet Access VPN, also known as PIA. Think of a VPN like building a force field around your internet connection. Without it, browsing online is like shouting secrets across a crowded room. Anyone nearby can listen in. PIA shields your personal data with powerful encryption, hiding your IP and keeping prying eyes, from hackers to advertisers and ISPs, out of your business. I've been using PIA for the better part of a decade now on my personal computer to help protect from all the hacking efforts that come with being a public figure. It's fast, easy to switch between servers in 91 countries, and one subscription covers every device in my house. It even helps you watch shows locked to other regions. So you want to explore the internet without fear of someone peeking over your shoulder, check out Private Internet Access. Use my link below for a huge 83% off. That's just $2.03 a month, with 4 extra months for free. Head over to piavpn.com/IsaacArthur to try it risk-free with their 30-day money-back guarantee. Defects and composites strengthen layers. Even the strongest materials have flaws. A crack, a wrinkle, a misaligned grain boundary. These defects can reduce a tether's strength dramatically. That's why real-world designs often turn to layered composites, stacks of graphene sheets interwoven with carbon nanotubes or bonded with polymers, spreading strain across multiple dimensions. For graphene, the more layers you have, the more the tether becomes resistant to fracture. Think of it less like a single rope and more like a woven tapestry, redundant, resilient, and resistant to catastrophic failure. Researchers are also exploring self-healing materials, embedding reactive layers that confuse tiny cracks under heat or radiation. We might even see robotic repair crawlers patrolling the ribbon, patching damage before it becomes dangerous. After all, it's not enough to build a miracle material, we have to keep it miraculous for decades at a time. Power and payload. Once the tether is in place, the next challenge is moving cargo and people up and down it efficiently. Powering climbers isn't just about propulsion, it's about energy delivery, conversion, and management. In most proposals, climbers are electrically driven, meaning they need a reliable, continuous power source for a journey that takes days. And as I mentioned earlier, we don't want to carry onboard fuel or batteries. That essentially makes you a rocket and subject to the tyranny of the rocket equation, the very thing we are seeking to circumvent with the elevator. The simplest method is to beam power from the ground via lasers or microwaves. A rectenna on the climber converts this into electricity. This sidesteps the need for heavy onboard batteries or fuel, but requires tight targeting, clear weather for a laser, and fail-safes for beam misalignment. Solar panels are another option, especially for the upper portions of the climb, but the panel area is limited and power needs are high. A more elegant long-term solution might be to run power directly through the tether itself. Graphene and carbon nanotubes are highly conductive, and a thick enough ribbon might double as a high-voltage power line, transmitting energy from the surface or from orbit, though this is not without issues, as Dennis Wright points out that a DC current will experience a sideways Lorentz force as the tether passes through the magnetosphere, which would push or strain the tether. Beamed or by wire, space-based solar arrays at the geostationary hub could feed this system, beaming energy to Earth and to climbers alike. Indeed, the huge cost advantage deploying solar arrays to geostationary with a space elevator may pay for an elevator many times over all by itself, and could be a big source of cargo for it. As for what we are lifting, early elevators will likely focus on cargo, fuel, construction materials, satellite components, maybe even water or food supplies. A typical climber might carry 10 to 60 tons. Passengers come later, as safety improves. A passenger car will need shielding from solar flares and cosmic rays, climate control, and comfort for a multi-day journey. Fast climbers will reduce the trip time and the need for heavy life support. And when cargo reaches the top, we don't just drop it into orbit. With a bit of extra tether extending past geostationary orbit, we can slingshot payloads to lunar orbit, Lagrange points, or even interplanetary trajectories. This turns the elevator into a launch pad for the solar system. Fueled spacecraft waiting at the counterweight can take over from there, never needing to touch Earth's gravity well. Safety, scaling, and the road ahead. Safety is paramount. A snap tether wouldn't fall to Earth like a whip. It would coil into orbit, possibly burning up, possibly making a mess of low Earth orbit. That's why redundancy matters, multiple tethers, replaceable segments, and robotic repair systems to help mitigate failures. The more modular and flexible the system, the safer it becomes. Climbers might have parachutes, emergency motors, or even escape pods for passenger versions. Segments of the tether could be designed to detach and fall harmlessly if compromised. Sensors embedded along the ribbon would monitor for heat, strain, or micrometeoroid impacts. And scaling is inevitable. Once the first elevator proves viable, demand will surge. Within decades we could see a dozen or more, with global coverage. Some will specialize in bulk cargo, others in people. Some may even be mobile, with anchor ships repositionable across the equator. Others could connect to suborbital rotavators or skyhooks, integrating with more exotic infrastructure. Non-equatorial tethers will be harder but not impossible. You might use counterweights or orbital rings to manage the forces. Such elevators could rise near major cities or industrial hubs, avoiding the need for sea-based anchors. That brings space access closer to population centers and the future closer to the present. And remember, the first elevator won't be the best. It will be the clunky one, the prototype, the Model T, but it paves the way. Future generations of tethers might lift tens of thousands of tons per day, running up and down like freight trains, and unlike rockets, they can operate continuously, quietly, and cleanly. The space elevator isn't just another launch system, it's a turning point, a transition from the age of exploration to the age of migration. It's a road to space, and once we lay that road with carbon and courage, the traffic is only going one way: up.